Welcome to Mastering Solutions. We don't have to draw a ray diagram with these ones. We're just asked to calculate the image position and the height. And with these ones, it's really important to remember the sign conventions. We'll start by calculating the position, and we're going to use the thin lens equation, which says that the power of a lens is equal to 1 over the focal length, which is also equal to 1 over the image distance plus 1 over the object distance. We're trying to figure this, right? So we'll minus over 1 over s. So we have 1 over s prime is equal to 1 over the focal length minus 1 over the object distance. Now, like I was saying, we need to remember the sign convention. And so with a diverging lens, remember that the focal length is always going to be negative, like they've indicated right here, which means that any power of a diverging lens is always going to be negative. We'll learn in the next chapter that that's how you correct someone's vision who is nearsighted. So if we plug these in, we have 1 over the image distance is equal to 1 over the focal length in meters, so a negative 0.2, and that is important to keep it in meters because a diopter is an inverse meter, so if it's not SI units, it won't work correctly. And that's over the object distance, which we said is 15 centimeters in front of a diverging lens, so we have 0.15. In front of the lens means it's upstream of the lens, and this will be a positive number for the object. So we have 1 divided by negative 0.2 minus 1 divided by positive 0.15. So that gives us a negative 11.67 diopters. So we have negative 11.67 diopters. We don't want diopters, we want meters. So if we take the reciprocal of the answer, that will give us in meters. So the image distance in this case is a negative 8.57 centimeters. So we could round that to 2 significant figures. So we have negative 8.6 centimeters. So that's our image distance right there. Now, if we move on to the height of the image, we're going to use the magnification equation for these ones. And that says that the height of the image divided by the height of the object is also equal to the negative image distance over object distance. And this section is what we'll be using, of course. We've done these on the past several problems. And so we're trying to solve for the image height. And so if we multiply both sides by h, that will isolate the image height, and that's h times negative s prime over s. So when we plug this in, the image height in meters is, the object height in meters is 2 centimeters tall. So putting that in meters, we'll just keep it this way. So 2 times 10 to the negative 2 meters. Multiplying that by the s prime, we do need to keep the negative here. This one comes from the equation. So we have negative 0.57 meters divided by the object distance, which we said was a positive 0.15, so 0.15 meters. So we have 2 times 10 to the negative 2, and that's multiplied by a negative times a negative 0.0857, and then that's divided by 0.15. All right, so that gives us in meters, and so we'll have 1, 2, so 1.14. So we have h prime, or the image height, is equal to 1.14 centimeters. Now that was a positive value, so that means that we have a virtual image that is upright, and it is virtual because it's on the same side as the object. That's what the negative indicates here. If it was real, this would be positive, meaning it's on the opposite side as the object. If this was negative here, that would mean it's inverted. So here are our answers: 8.6 centimeters on the same side as the object, and 1.14 centimeters tall, that is upright.